They're faster than light, they might move backward through time, and for decades, physicists dismissed them as mathematical nonsense. But in 2024, everything changed. This is the tachyon, and today, we're diving deep into one of physics' most controversial ideas, particles that travel faster than light itself. And here is a question for you. If you could witness any moment in cosmic history, what would it be? The Big Bang? The first star? Or perhaps something else? Let me know in the comments. I will pin the most creative answer. Now let's begin. The word tachyon comes from the Greek word tachys, meaning fast or swift. These hypothetical particles were first seriously proposed in the 1960s by physicists like Gerald Feinberg, who wondered whether relativity actually forbids faster-than-light particles or simply forbids ordinary particles from accelerating past light speed. Turns out there's a loophole. Einstein's equations don't say particles can't exist beyond the light barrier, they say particles can't cross it. Think of it like three separate lanes on a cosmic highway. One lane for particles moving slower than light like you and me and everything we see around us. Another lane for particles moving exactly at light speed, like photons. And a third, mysterious lane for particles that always move faster than light. Tachyons would occupy that third lane, forever racing ahead, unable to slow down to our familiar speeds. Now, before we go further, let me be crystal clear about something crucial. Tachyons are purely theoretical. Despite decades of searching, no experiment has ever detected a tachyon, no telescope has spotted one, no particle accelerator has produced one. They remain in the realm of mathematical possibility, living only in equations and thought experiments. But that doesn't make them any less important. Throughout history, theoretical physics has predicted particles and phenomena long before we had the technology to observe them. The Higgs boson was predicted in 1964, but wasn't confirmed until 2012 at CERN's Large Hadron Collider. Gravitational waves were predicted by Einstein in 1916 but weren't directly detected until 2015 by LIGO. So the absence of evidence isn't always evidence of absence, especially when we're talking about particles that might interact with ordinary matter in incredibly subtle ways, if at all. Let's dig into what makes tachyons so weird. According to relativity, as an ordinary particle speeds up, its mass effectively increases, requiring more and more energy to accelerate further. As you approach light speed, your mass approaches infinity, meaning you'd need infinite energy to actually reach it. That's why the light barrier exists for us. But tachyons flip this relationship on its head. For a tachyon, slowing down requires energy. The less energy a tachyon has, the faster it goes. At zero energy, a tachyon would be moving at infinite speed, everywhere in the universe simultaneously. As you add energy, it slows down, but it can never decelerate enough to drop below light speed. It's trapped in the fast lane, just as we're trapped in the slow lane. This inverted relationship creates some truly mind-bending consequences. One of the most famous involves causality, the principle that causes must come before their effects. If tachyons exist and can carry information, you could theoretically send a message into your own past. Here's a simplified version of how that might work. Imagine you send a tachyon signal from Earth to a spaceship moving away from you at high speed. From your perspective, the signal arrives at the ship in the future. But because of how relativity treats different reference frames, from the ship's perspective, it might receive the signal before you sent it. The crew could then send a tachyon signal back to Earth, and you might receive their reply before you even transmitted your original message. This creates what physicists call a closed time-like curve, essentially a loop in time. You could potentially send yourself a message saying, "Don't send this message," creating a logical paradox that makes philosophers and physicists lose sleep. For decades, this causality problem made tachyons seem impossible, almost absurd. How could the universe allow particles that let you become your own grandfather, preventing your own birth, through some convoluted sequence of faster-than-light signals. Many physicists dismiss tachyons as mathematical curiosities, interesting on paper but physically meaningless. The general attitude was that if your theory predicts tachyons, something has gone wrong. They were the enfants terribles of modern physics, the troublemakers that nobody wanted at the party. But here's where our story takes a fascinating turn. In 2024, a groundbreaking study published in Physical Review D by physicists from the University of Warsaw and the University of Oxford challenged everything we thought we knew about tachyons. Led by Andrzej Dragan, the research team discovered that all those problems with tachyons, all those paradoxes and contradictions, they weren't problems with tachyons themselves. They were problems with how we were doing the calculations. The researchers found that physicists had been applying what are called boundary conditions incorrectly when working with tachyon equations. Let me explain what that means. If you're enjoying this deep dive into the cosmos and want to support the channel, hit that subscribe button and give this video a thumbs up. It really helps me bring more content like this to curious minds like yours. Now let's continue unraveling this mystery. When physicists model any system, they need to specify its starting conditions, where things are, how fast they're moving, what their properties are at the beginning of time, or at least at the beginning of your calculation. These are called initial boundary conditions. For almost every situation in physics, specifying just the initial conditions is enough. You plug in where everything starts, apply the laws of physics, and you can predict where everything will be in the future. This works beautifully for planets orbiting stars, for balls thrown through the air, for electrons zipping through circuits. But Dragan and his colleagues realized that tachyons are fundamentally different. Because tachyons can, in principle, influence their own past, you can't just specify initial conditions. You also need to specify final conditions, where things end up, what the system looks like at the end of time, or at least at the end of your calculation. This might sound bizarre, but think about it like watching a movie. Normally, we watch from beginning to end, and the story unfolds logically. But imagine a movie so well crafted that you could watch it backward, from end to beginning, and it would still make perfect sense, telling a complete and logical story. That's kind of how tachyon physics works when you apply both initial and final boundary conditions. You're not just asking, where did this come from, but also, where is this going? And when you do that, all those paradoxes start to disappear. The Warsaw-Oxford team's discovery didn't just patch a hole in tachyon theory, it fundamentally transformed our understanding of what these particles could mean for physics. When they incorporated both initial and final boundary conditions into their calculations, three major problems that had haunted tachyon physics for decades simply vanished. Let me walk you through each one. The first problem was called tachyon condensation, or the avalanche problem. Previous calculations suggested that if even one tachyon existed, the vacuum of space would become unstable. Tachyons would spontaneously create more tachyons, which would create even more, cascading into an infinite avalanche of particles flooding the universe. Obviously, we don't see this happening, so physicists concluded tachyons couldn't exist. But when Dragan's team applied proper boundary conditions considering both past and future states, they found that the vacuum remains perfectly stable, no avalanche. The ground state of a tachyon field, the lowest energy configuration, doesn't collapse. It sits there peacefully, consistent with the universe we observe around us. The second problem involved something called observer dependence. In relativity, different observers moving at different speeds see the world differently. Time passes at different rates, lengths contract, simultaneity breaks down. But everyone should agree on certain fundamental facts, like how many particles exist. 7 particles should be 7 particles whether you're standing still or flying past at 90% light speed. Yet old tachyon calculations suggested that changing your reference frame would change the number of tachyons you observe. This violated a basic principle of physics. Objective reality shouldn't depend on who's looking. The new research showed this problem also evaporates when you properly account for boundary conditions. The number of tachyons remains consistent across all reference frames. Reality stays objective. The third problem was negative energy. In earlier formulations, tachyons seem to possess negative energy, which creates enormous theoretical headaches. Negative energy suggests the vacuum isn't really empty but filled with positive energy that particles could borrow against, potentially allowing perpetual motion machines or causing space itself to decay. These issues are so severe that most physicists view negative energy as a red flag, indicating something has gone deeply wrong with your theory. But again, with the corrected mathematical framework, tachyons no longer require negative energy. They fit cleanly into the energy budget of the universe without breaking thermodynamics or destabilizing reality. This 2024 breakthrough essentially rehabilitated tachyons from impossible troublemakers to legitimate theoretical possibilities. It doesn't prove tachyons exist, but it proves they could exist without violating the laws of physics as we understand them. That's a monumental shift. It means when we're cataloging what the universe might contain, we can't dismiss faster-than-light particles out of hand anymore. They're back on the table, and that opens up incredible questions. So where might tachyons be hiding? If they're allowed by physics, why haven't we found them? One possibility is that tachyons simply don't interact very strongly with ordinary matter. Think about neutrinos, those ghostly particles produced in nuclear reactions. Trillions of neutrinos pass through your body every second, streaming from the sun, and you never feel a thing because they barely interact with anything. They can pass through the entire Earth as if it weren't there. It took decades of sophisticated experiments to detect neutrinos despite them being everywhere. Tachyons might be even more elusive if they don't carry electric charge, if they don't participate in the strong nuclear force, if they only interact gravitationally or through some unknown force. They could be extraordinarily difficult to detect, even if they're common. Another intriguing possibility involves neutrinos themselves. And actually, speaking of understanding particles at extreme speeds, if you want to explore what happens when we push matter toward the light barrier from our side, check out my video called What Actually Happens If We Reach Light Speed, where we dive into the wild physics of approaching that cosmic speed limit. The link is in the description and on the card above, and I think you'll find it fascinating as a companion to today's discussion. But back to neutrinos and tachyons. Neutrinos are among the strangest particles in the standard model of physics. They come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They oscillate between these flavors as they travel, a phenomenon that won the Nobel Prize in 2015. For this oscillation to work mathematically, neutrinos must have mass, but incredibly tiny mass, far smaller than even electrons. For years, experiments have tried to measure exactly how much mass neutrinos have, and the results have been puzzling. Some experiments, like the Katrin experiment that began taking data in 2019, have placed upper limits on neutrino mass. The most recent results suggest the electron neutrino has a mass of less than 0.7 electron volts, which is about 1/1,000,000th the mass of an electron. But here's where things get interesting. Some measurements have just hinted at something strange: the possibility that neutrinos might have imaginary mass. Remember, imaginary doesn't mean fake in mathematics. It means involving the square root of -1, written as I. And particles with imaginary mass are, by definition, tachyons. Could neutrinos, which we know exist and which we detect every day in laboratories around the world, actually be tachyons? Could they be traveling faster than light? Before you get too excited, I need to pump the brakes here. The evidence for tachyonic neutrinos is extremely controversial and far from conclusive. Most neutrino physicists would tell you the data is more consistent with neutrinos having small positive mass, not imaginary mass. But the possibility hasn't been completely ruled out. A paper published in 2022 by Robert Ehrlich reviewed the experimental landscape and argued that certain anomalies in cosmic ray data and supernova neutrino detections might be explained if at least some neutrino types are tachyons. In 2011, the Opera experiment at CERN made headlines by claiming they'd measured neutrinos traveling faster than light. The physics community went into overdrive, with thousands of papers written trying to explain or debunk the result. Ultimately, in 2012, the Opera collaboration announced they'd found the problem. A faulty fiber optic cable in their timing system had created a measurement error. The neutrinos weren't actually faster than light after all. That episode is instructive because it shows how extraordinary claims require extraordinary evidence. If neutrinos were tachyons, it would revolutionize physics, so we need to be absolutely certain before accepting such a conclusion. Current experiments like Katrin and the upcoming Project 8, which promises even better precision, will continue narrowing down neutrino properties. If neutrinos do turn out to have imaginary mass, it would be one of the most stunning discoveries in the history of science, proving that tachyons aren't just mathematical abstractions, but real particles we've been detecting for decades without realizing their true nature. There's another cosmic mystery where tachyons might play a role: dark matter. This invisible substance makes up about 85% of all matter in the universe. We know it exists because we see its gravitational effects. Galaxies rotate too fast to hold together based on the visible matter alone. Something invisible is providing extra gravity, and we call that something dark matter. Despite decades of searching, we haven't identified what dark matter actually is. It doesn't emit light, doesn't absorb light, doesn't seem to interact with ordinary matter except through gravity. Physicists have proposed countless candidates: weakly interacting massive particles called WIMPs, ultralight particles called axions, primordial black holes, and many others. None have been confirmed. In 2024, a fascinating study suggested a radical idea. What if dark matter is made of tachyons? At first, this sounds crazy. How could faster-than-light particles provide the gravitational glue holding galaxies together? But the researchers demonstrated that a universe filled with tachyonic matter would behave in very specific ways. As the universe expands, tachyonic matter could cause the expansion to first decelerate, then accelerate, which matches what we observe. Our universe spent billions of years expanding but slowing down due to gravity. Then about 5 billion years ago, the expansion started accelerating, driven by something we call dark energy. The tachyon model could potentially explain both dark matter and dark energy as different manifestations of the same underlying physics. To test this idea, the researchers compared their tachyon model against observations of type Ia supernovae. These exploding stars serve as standard candles in cosmology, objects whose true brightness we know, allowing us to calculate how far away they are and how fast the universe is expanding at different times in cosmic history. Amazingly, the tachyon model fit the supernova data just as well as the standard cosmological model that uses separate components for dark matter and dark energy. This doesn't prove dark matter is tachyons, but it shows the idea is viable and makes testable predictions. However, a paper published in January 2025 by researchers Mark Hertzberg, Abraham Loeb, and Aidan Morehouse threw cold water on the idea of heavy tachyons. They studied what would happen if tachyons existed near black holes. Black holes emit Hawking radiation, a quantum effect where particle-antiparticle pairs spontaneously form at the event horizon, with one particle escaping and the other falling in. This causes black holes to slowly evaporate over immense timescales. The researchers calculated that if heavy tachyons exist, black holes would radiate them away much more efficiently than ordinary particles, causing black holes to evaporate far faster than observed. Since we see black holes that have existed for billions of years, this places strict limits on how massive tachyons can be. Specifically, they found that tachyons can't be heavier than about 3 × 10 to the 9th power gigaelectronvolts, or 3 billion electron volts. That's still an enormous energy, far beyond what we can produce in particle accelerators, but it rules out tachyons at the scales where we'd expect to see effects from quantum gravity or grand unification theories. What's crucial to understand is that these aren't just abstract mathematical games physicists play for fun. These are serious attempts to understand the fundamental nature of reality, grounded in observation and experiment. Every theoretical proposal must eventually face the court of empirical evidence. Tachyons remain on trial, and the jury is still deliberating. But the fact that we're even having this conversation, that modern physics can accommodate faster-than-light particles without collapsing into logical contradictions, tells us something profound about how far we've come in understanding the universe. Let me take you back to the causality issue because it's both the most troubling and the most fascinating aspect of tachyon physics. The idea that you could send information into your own past feels like it should break the universe. Philosophers have puzzled over time travel paradoxes for generations. The classic example is the grandfather paradox. You travel back in time and prevent your grandparents from meeting, which means you're never born, which means you can't travel back in time, which means your grandparents do meet, which means you are born, which means you can travel back in time, and round we go in an infinite loop of contradiction. But some physicists argue that these paradoxes might not be as devastating as they seem. One resolution involves what's called the Stuckelberg-Feynman reinterpretation principle, named after Ernst Stuckelberg and Richard Feynman, two giants of 20th century physics. This principle suggests that a particle moving backward in time is mathematically equivalent to its antiparticle moving forward in time. Every particle has an antiparticle with opposite properties. An electron has a positively charged antiparticle called a positron, a proton has an antiproton, and so on. According to this reinterpretation, when a tachyon appears to violate causality by moving backward in time, what's actually happening is an anti-tachyon moving forward in time. Think of it like watching a movie run backward. A person walking backward out of a room looks strange but isn't paradoxical. You can reinterpret it as a different person walking forward into the room. The mathematics work out the same either way. This doesn't completely solve all causality issues, but it suggests that what looks like time travel from one perspective might just be ordinary forward-in-time physics from another perspective. The universe might be more clever than we are at avoiding paradoxes. Another approach to the causality problem involves embracing what's called retrocausality, the idea that future events can influence past events. This sounds insane to our everyday intuition, where time flows in one direction and the future grows out of the past, not the other way around. But quantum mechanics already has hints of retrocausality. In certain interpretations of quantum theory, the act of measuring a particle now affects the state that particle had in the past. The famous double-slit experiment shows interference patterns that seem to depend on whether we measure which path a particle took, even if we make that measurement after the particle has already passed through the slits. It's as if the particle knows in advance whether we're going to measure it. If retrocausality is a genuine feature of nature at the quantum level, then tachyons might simply be making that feature more obvious at larger scales. The requirement to specify both initial and final boundary conditions, which Dragan and his team emphasized, fits naturally into a retrocausal framework. The future constrains the past just as much as the past constrains the future. Time becomes less like a river flowing in one direction and more like a tightly woven tapestry, where every thread influences every other thread, regardless of their position, along the temporal axis. Now, I know what some of you are thinking. This all sounds completely detached from reality. We experience time flowing forward, not backward. Causes always precede effects in our daily lives. You can't unbreak an egg. You can't unsay a word. You can't reverse aging. How can physics seriously entertain ideas that seem to contradict our most basic experiences? The answer is that physics has a long history of revealing that the universe operates very differently at fundamental levels than it appears to in our everyday experience. Objects aren't solid, they're mostly empty space with tiny electrons buzzing around atomic nuclei. Matter isn't continuous, it's quantized into discrete packets. Time isn't absolute, it flows at different rates, depending on how fast you're moving and how strong the gravitational field is around you. Space isn't flat, it curves in the presence of mass and energy. Every one of those statements would have sounded absurd to someone living 200 years ago, yet we now know they're true because experiments confirm them. The universe doesn't care about our intuitions. It operates according to mathematical principles that often defy common sense. So when physicists propose that particles might travel faster than light, or that effects might precede causes, we shouldn't dismiss these ideas just because they feel wrong. We should test them, probe them, and follow the evidence wherever it leads. So how might we actually detect tachyons if they exist? This is one of the biggest challenges facing researchers. Traditional particle detectors work by measuring the energy, momentum, and other properties of particles as they interact with matter. Detectors at places like CERN use magnetic fields to bend the paths of charged particles, allowing physicists to identify them based on their curvature. They use calorimeters that absorb particle energy and measure it, tracking chambers that record particle trajectories, and sophisticated timing systems that measure when particles arrive. But all of these techniques assume particles are moving slower than light. A tachyon racing through a detector faster than light would create unique signatures that our current detectors aren't designed to recognize. One possibility is Cherenkov radiation, named after Soviet physicist Pavel Cherenkov. When charged particles move through a medium faster than light travels in that medium, they emit a characteristic blue glow. This happens regularly in nuclear reactors, where electrons move faster than light travels through water, though still slower than light travels through vacuum. If tachyons carry electric charge and move faster than light even in vacuum, they might emit a vacuum Cherenkov radiation, a never-before-seen phenomenon that would be a smoking gun signature. Another detection strategy involves looking for particles that appear to arrive before they're created. Imagine a cosmic ray, a high-energy particle from space, hitting Earth's atmosphere and creating a shower of secondary particles. Normally, we detect these secondary particles shortly after the cosmic ray arrives, but if some of those secondary particles are tachyons, they might reach our detectors before the cosmic ray that created them hits the atmosphere. We'd see the effect before the cause, a clear violation of ordinary causality that would indicate something extraordinary is happening. Researchers have also proposed searching for tachyons in the cosmic neutrino background. Just as the universe is filled with cosmic microwave background radiation, the afterglow of the Big Bang, it should also be filled with a background of neutrinos created in the early universe. These relic neutrinos have been traveling through space for nearly 14 billion years, and if some of them are actually tachyons, they might have properties we can detect. The challenge is that these background neutrinos have incredibly low energy, making them nearly impossible to interact with. Current technology can't detect them directly, but future experiments might develop the sensitivity needed. There's also the possibility of indirect detection through cosmological observations. If tachyons played a role in the early universe during cosmic inflation or the formation of the first structures, they might have left imprints on the cosmic microwave background or on the distribution of galaxies we see today. Teams of cosmologists analyze maps of the universe looking for subtle patterns that could reveal new physics. Most of these patterns would point to ordinary slow-moving particles, but certain specific signatures could indicate tachyonic influence. For example, if tachyons contribute to dark matter, the way galaxies cluster, and the way light from distant galaxies bends around massive structures might show tiny deviations from standard predictions. Some of the most intriguing searches involve neutrino astronomy. We've entered an era where we don't just study the universe with light across the electromagnetic spectrum from radio waves to gamma rays. We also use neutrinos and gravitational waves as cosmic messengers. In 2017, the IceCube Neutrino Observatory, a detector buried deep in Antarctic ice, traced a high-energy neutrino back to a blazar, a supermassive black hole shooting jets of material toward Earth from 4 billion light-years away. This opened a new window on the universe, allowing us to study cosmic events that are hidden from traditional telescopes. If neutrinos are tachyons, they might reach Earth slightly before light from the same event. This is testable. When a supernova explodes, it releases a tremendous burst of neutrinos followed by light. The neutrinos actually emerge first anyway, because they escape the star's core immediately, while light takes hours to diffuse outward. But if neutrinos are tachyons, the time difference would be slightly larger than expected based on their journey through the star. By carefully measuring arrival times of neutrinos and photons from the same supernova, we could potentially detect this tachyonic signature. The challenge is that supernovae in our galaxy are rare. The last one visible to the naked eye was in 1604, over 400 years ago. We detected neutrinos from supernova 1987A in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way, and those measurements were consistent with neutrinos traveling at light speed or just below. But the statistics were limited. A supernova in our own galaxy, detected by modern instruments, could provide the precision needed to settle the question. There are also laboratory experiments that could, in principle, create tachyons if they exist, and if they interact with ordinary matter strongly enough. Particle accelerators smash protons together at energies reaching trillions of electron volts, momentarily recreating conditions similar to those fractions of a second after the Big Bang. Out of these collisions emerge showers of particles, most of which are well understood: quarks, gluons, electrons, photons, and so on. But physicists are always looking for anomalies, unexpected particles, or behaviors that don't fit the standard model. If tachyons can be created in high-energy collisions, they might show up as missing energy or missing momentum, situations where the accounting doesn't add up because something escaped the detector too quickly to register. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, has been searching for new physics since it began operations in 2008. It famously discovered the Higgs boson in 2012, confirming the final missing piece of the standard model. But physicists hope to find much more: supersymmetric particles, extra dimensions, dark matter candidates, and yes, potentially tachyons. Every collision is analyzed in excruciating detail, with sophisticated algorithms sorting through petabytes of data looking for anything unusual. So far, the LHC has seen nothing beyond the standard model, which is both disappointing and interesting. It tells us that new physics, whatever it is, must be either at higher energies than we can currently reach, or interacting so weakly that we haven't noticed it yet. This brings us to a fundamental question about the nature of scientific inquiry. How do you search for something when you're not entirely sure what you're looking for? Tachyons are especially tricky because different theoretical frameworks make different predictions about their properties. Some theories suggest tachyons would be electrically neutral, making them invisible to electromagnetic detectors. Others propose they might carry charge. Some frameworks predict tachyons would have spin 0, behaving like the Higgs boson, while others allow for tachyons with higher spin. Some theories suggest tachyons would be fundamental particles, while others propose they might be composite objects made of other particles bound together in exotic ways. Without knowing which version is correct, experimentalists have to cast a wide net, searching for multiple possible signatures simultaneously. This is expensive, time-consuming, and requires enormous patience. But it's also how science progresses. You form hypotheses, design tests, collect data, and let nature tell you what's true. Sometimes nature surprises you. The discovery of the cosmic microwave background in 1965 was accidental. Arno Penzias and Robert Wilson were trying to eliminate noise from their radio antenna when they realized the noise was actually the echo of the Big Bang. Sometimes you find what you weren't looking for, and it transforms our understanding of everything. The theoretical framework for tachyons has evolved considerably since the 1960s. Early papers by Gerald Feinberg treated tachyons as individual particles obeying special relativity with imaginary mass. Later work by physicists like Erasmo Recami explored how tachyons would behave in quantum field theory, the mathematical framework that describes how particles and fields interact. Recami and others showed that many of the apparent paradoxes of tachyons could be resolved through careful analysis of quantum mechanics and causality. They demonstrated that tachyons wouldn't necessarily allow you to send useful information into the past, preserving causality in a practical sense, even if the mathematical structure looked strange. More recent work has connected tachyons to string theory, the ambitious attempt to unify all forces and particles into a single theoretical framework. In string theory, particles aren't point-like objects but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. Some string theories predict the existence of tachyonic modes, certain vibration patterns that correspond to faster-than-light particles. Interestingly, when tachyons appear in string theory, they often signal that the vacuum state is unstable, that the universe wants to transition to a different configuration. This tachyon condensation can drive important physical processes like the breaking of symmetries that gave particles their masses in the early universe. The Higgs field, which permeates all of space and gives particles their mass, went through a tachyon condensation process in the early universe. Initially, the Higgs field was in an unstable state. Then it underwent a phase transition, like water freezing into ice, settling into a stable configuration with non-zero value everywhere. This transition is mathematically similar to tachyon condensation, though the Higgs itself isn't a tachyon in the sense of traveling faster than light. The point is that tachyonic behavior in field theory can drive real physical processes, even if actual tachyon particles don't emerge as final products. This connection between tachyons and symmetry breaking hints at something profound. Perhaps tachyons aren't separate exotic particles we need to discover, but rather mathematical descriptions of how fields behave during transitions. The early universe was a seething cauldron of energy where fields underwent rapid changes as the cosmos expanded and cooled. Inflation, the exponential expansion that occurred in the first fraction of a second after the Big Bang, might have been driven by a field with tachyonic properties. Grand, unified theories, which attempt to merge the electromagnetic, weak and strong nuclear forces into a single force that split apart as the universe cooled, might involve tachyonic transitions at energy scales far beyond what we can probe directly. If tachyons played a role in the early universe, they might have left fingerprints we can still see today. The cosmic microwave background, that faint glow of radiation filling the universe, carries information about conditions when the universe was only 380,000 years old. Tiny fluctuations in this radiation, hot and cold spots less than 1 part in 100,000 different from average. Tell us about quantum fluctuations in the early universe that eventually grew into galaxies and galaxy clusters. If tachyonic fields contributed to these fluctuations, they would imprint specific patterns that cosmologists could potentially identify. Missions like the Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. The data has been analyzed exhaustively, testing countless theoretical predictions. So far, the results are remarkably consistent with the simplest models of inflation, driven by a single slow-rolling field, no tachyons required. But there are still anomalies, small puzzles, that don't quite fit standard models. The cold spot, an unusually large cold region in the southern sky, has no convincing explanation. The axis of evil, a suspicious alignment of large-scale fluctuations, challenges the assumption that the universe is statistically uniform in all directions. Some physicists have speculated that these anomalies might hint at exotic physics in the early universe, possibly including tachyonic contributions, though these ideas remain highly speculative. Another cosmic mystery where tachyons might matter involves the nature of time itself. We experience time as flowing from past to future, and the laws of physics seem to incorporate this arrow of time through the second law of thermodynamics. Entropy, or disorder, always increases. A broken glass doesn't spontaneously reassemble. Heat flows from hot objects to cold objects, never the reverse. Memory works in one direction. We remember the past, not the future. Yet the fundamental equations of physics, including relativity and quantum mechanics, are largely time-symmetric. They work just as well running forward or backward. So where does the arrow of time come from? Some physicists argue it emerges from initial conditions. The universe started in an extremely low entropy state at the Big Bang, highly ordered and uniform. As it evolved, entropy increased, creating the arrow of time we experience. But this explanation is incomplete because it doesn't explain why the initial conditions were so special. Why did the universe start in such an unlikely configuration? Tachyons, with their ability to connect future and past, might offer new perspectives on this question. If the future constrains the past just as much as the past constrains the future, if retro-causality is built into the fabric of space-time, then perhaps the arrow of time isn't as fundamental as we think. Perhaps it's an emergent property, something that appears at large scales but dissolves when you look closely at the quantum level where tachyons might operate. These are deep philosophical waters, and it's important to acknowledge that we're speculating here, exploring possibilities rather than established facts. But this is how science advances, especially at the frontiers, where we're pushing beyond what we know into what we might discover. Every great breakthrough in physics started as speculation. Atoms were philosophical speculation for 2,000 years before we confirmed they exist. Black holes were mathematical curiosities in Einstein's equations before astronomers found them. The expansion of the universe seemed absurd until Edwin Hubble observed galaxies racing away from us in 1929. The key is that speculation in science isn't random guessing. It's informed by mathematics, constrained by observation, and always subject to experimental test. When Andrzej Dragan and his team published their 2024 paper showing tachyons are compatible with relativity, they weren't just offering an opinion. They solved equations, identified mistakes in previous calculations, and produced results that other physicists could check and verify. The paper went through peer review, where expert researchers scrutinized every claim before publication in Physical Review D. This process isn't perfect, but it's designed to filter out errors and ensure that new ideas meet rigorous standards. Science is fundamentally a conversation, a collective human endeavor where researchers around the world build on each other's work, challenge each other's conclusions, and gradually converge on truth through the accumulation of evidence. No single paper proves anything definitively. Instead, each paper is a piece of a larger puzzle. The Warsaw-Oxford team contributed an important piece by showing tachyons aren't ruled out by theory. Now other researchers need to contribute additional pieces, better experimental searches, refined theoretical predictions, new observational tests. Over time, the puzzle will resolve into a clearer picture, and we'll know whether tachyons are real or merely mathematical possibilities that nature chose not to implement. There's something beautifully human about this quest to understand the universe at its most fundamental level. We're tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, yet we can use our minds to probe the nature of reality itself. We can conceive of particles that travel faster than light, develop mathematical frameworks to describe them, design experiments to search for them, and debate their implications for the cosmos. This is what makes us human, not just our ability to survive and reproduce, but our relentless curiosity about how things work and where we fit in the grand scheme of existence. When you look up at the night sky, you're seeing photons that traveled for years, centuries, or even billions of years to reach your eyes. Each photon carries information about the object that emitted it, about the space it traveled through, about the state of the universe at the time it began its journey. Astronomers are cosmic archaeologists decoding these messages to reconstruct the history of everything. And if tachyons exist, they're carrying messages too, perhaps even more exotic messages about regions of space-time we can't access any other way. Imagine for a moment that we do discover tachyons. What would that mean for the future of humanity? The implications would be staggering, touching everything from our understanding of fundamental physics to potential technologies we can barely imagine. If tachyons exist and we learn to detect them, we'd have access to a completely new channel of information about the universe. Just as radio astronomy revolutionized our view of the cosmos in the mid-20th century, revealing active galaxies, pulsars, and the cosmic microwave background, tachyon astronomy could unveil phenomena completely invisible to all our current instruments. Consider how different messengers give us different windows on the universe. Optical telescopes show us stars, galaxies, and nebulae in visible light. Radio telescopes reveal cold gas clouds, energetic jets from black holes, and the structure of magnetic fields. Infrared telescopes peer through dust to see star formation and distant galaxies reddened by cosmic expansion. X-ray and gamma-ray telescopes spot violent processes, supernova remnants, neutron stars, black holes devouring matter. Gravitational wave detectors like LIGO and Virgo sense ripples in space-time from colliding black holes and neutron stars billions of light-years away. Neutrino detectors catch ghostly particles from the cores of stars and supernovae. Each new messenger has revealed surprises. Before radio astronomy, we had no idea that galaxies could shoot jets of particles millions of light-years into space. Before X-ray astronomy, we didn't know neutron stars existed. Before gravitational wave astronomy, we couldn't study black hole mergers directly. What might tachyon astronomy reveal? Perhaps phenomena occurring at speeds we can't currently observe, processes in the early universe that left no trace except through tachyonic signatures, or even messages from advanced civilizations using faster-than-light communication if such technology is possible. That last point touches on one of humanity's most profound questions. Are we alone in the universe? The Fermi paradox asks why, if the galaxy is billions of years old and contains hundreds of billions of stars, we haven't detected any signs of alien civilizations. Many explanations have been proposed. Perhaps life is extraordinarily rare, or intelligence is uncommon, or technological civilizations tend to destroy themselves quickly. But another possibility is that we're simply looking in the wrong way. If advanced civilizations use tachyonic communication instead of electromagnetic signals, we'd never detect their messages with our current radio telescopes. We'd be like someone trying to receive emails using a telegraph machine, completely unable to access the actual communication channel. The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for artificial radio signals since the 1960s. Projects like Breakthrough Listen, funded by philanthropist Yuri Milner and launched in 2015, use the world's most powerful telescopes to search millions of stars across a wide range of frequencies. So far, nothing conclusive has been found. Every promising signal has turned out to be interference, a natural phenomenon, or a misidentification. Some researchers argue we should expand our search strategies to include other possible communication methods, optical laser pulses, atmospheric biomarkers on exoplanets, megastructures like Dyson spheres, and, yes, potentially tachyonic signals if we could figure out how to detect them. But let's be careful not to get too carried away with speculation. The vast majority of physicists would tell you that even if tachyons exist, using them for practical communication faces enormous, probably insurmountable challenges. Creating tachyons would likely require tremendous energy. Controlling them, directing them to specific destinations, encoding information in them, and detecting them at the receiving end would all present formidable technical obstacles. And the causality issues, even if they don't lead to logical paradoxes, would make tachyonic communication extremely strange from a practical standpoint. How do you have a conversation when the reply might arrive before you send your message? Still, the history of technology is full of things that seemed impossible until someone figured out how to do them. Heavier-than-air flight was considered impossible by many experts in the late 19th century. Splitting the atom to release nuclear energy seemed like fantasy until 1938. Landing humans on the moon was science fiction until 1969. Global, instantaneous communication through devices small enough to fit in your pocket would have seemed like magic to someone living in the 19th century. So while we should be skeptical of wild claims, we should also remain open to possibilities that seem far-fetched today, but might become reality tomorrow. Let's ground ourselves again in what we actually know rather than what we imagine. The state of tachyon physics in 2026 is this: theoretically possible, but experimentally unconfirmed. The recent mathematical work has shown that tachyons don't violate fundamental physical principles when properly analyzed. This is important because it means tachyons belong on the list of legitimate theoretical possibilities that deserve serious investigation rather than being dismissed as nonsense. However, absence of evidence isn't evidence of absence, but it's also not evidence of presence. We have no confirmed detection of tachyons from any experiment or observation, despite decades of looking. This puts tachyons in an interesting category alongside other hypothetical particles and phenomena. Magnetic monopoles, particles with only a north or south magnetic pole rather than both, are allowed by physics and predicted by some theories, but have never been found despite extensive searches. Tachyons, ultralight particles proposed to solve certain problems in particle physics and potentially make up dark matter, remain undetected, though experiments are actively hunting for them. Primordial black holes, tiny black holes that might have formed in the early universe, could exist but haven't been conclusively identified. All of these are theoretically motivated, mathematically consistent, and empirically elusive. The experimental search for tachyons continues in various forms. One approach involves analyzing data from existing experiments and observations with fresh eyes, looking for signatures that might have been overlooked or misinterpreted. The archives of particle physics experiments contain petabytes of data from decades of running various detectors. Most of this data has been analyzed for specific purposes, searching for particular particles or measuring specific properties. But reanalyzing it with tachyons in mind, looking for anomalous timing signatures or missing energy patterns consistent with faster-than-light particles, could potentially reveal something new. This is detective work, sifting through mountains of information for tiny clues that everyone else missed. Another approach involves designing new experiments specifically targeting tachyonic signatures. These experiments might use advanced timing systems capable of measuring arrival times with picosecond precision, 1/trillionth of a second. They might employ novel detector geometries designed to catch particles arriving from unexpected directions or at unexpected times. They might correlate observations from widely separated detectors, looking for particles that appear to travel between them faster than light could. Some proposals even suggest space-based experiments, placing detectors in orbit or on the Moon where they'd be free from atmospheric interference and could monitor larger volumes of space. There's also the intriguing possibility of using black holes as natural laboratories for tachyon physics. That January 2025 paper by Hertzberg, Loeb, and Morehouse that I mentioned earlier calculated how black holes would interact with tachyons. While their results constrained heavy tachyons by showing that black holes would evaporate too quickly if such particles existed, the same analysis suggests that observing black holes carefully could reveal lighter tachyons if they're out there. Black holes are among the most extreme objects in the universe, with gravitational fields so intense that they warp space-time into knots. If tachyons interact gravitationally, black holes should affect them in detectable ways. The Event Horizon Telescope collaboration, which produced the first image of a black hole's shadow in 2019, continues to observe supermassive black holes in exquisite detail. These observations focus on the region immediately around the event horizon where space-time curvature is strongest and where unusual physics might manifest. If tachyons are produced or affected by the extreme conditions near black holes, future observations with improved resolution might spot anomalies, material appearing to move faster than expected, timing discrepancies in the motion of hot gas orbiting the black hole, or unexpected patterns in the radiation emitted from the accretion disk. Stellar mass black holes formed from collapsed stars present another opportunity. When two black holes merge, they release tremendous energy in gravitational waves, ripples in spacetime that LIGO and Virgo detect. These mergers also potentially produce other particles, neutrinos, perhaps photons in gamma-ray bursts, and potentially tachyons if conditions are right. By coordinating gravitational wave detectors with other instruments, astronomers can perform multi-messenger astronomy, observing the same event through different channels. A black hole merger observed simultaneously in gravitational waves, electromagnetic radiation, neutrinos, and hypothetically tachyons would provide an incredibly rich dataset for testing fundamental physics. We're living in a golden age of astronomy where new discoveries arrive almost weekly. Missions like the James Webb Space Telescope, launched on Christmas Day 2021, are revolutionizing our view of the universe. Webb has peered farther back in cosmic time than ever before, imaging galaxies as they appeared just a few 100 million years after the Big Bang. It's studying the atmospheres of exoplanets, searching for signs of water vapor, methane, and other molecules that might indicate habitability or even life. It's observing star formation in unprecedented detail, tracking how clouds of gas and dust collapse to ignite nuclear fusion. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will conduct enormous surveys of the sky, imaging billions of galaxies to map the large-scale structure of the universe and search for exoplanets through gravitational microlensing. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations soon, photographing the entire visible sky every few nights to create an enormous movie of the changing universe. It will discover millions of asteroids, track variable stars, catch supernovae shortly after they explode, and potentially spot all sorts of transient phenomena we've never seen before. Each of these missions produces vast amounts of data that needs to be analyzed. Astronomers use sophisticated algorithms and increasingly artificial intelligence to process the information, searching for patterns and anomalies. It's entirely possible that signatures of exotic physics, potentially including tachyons, already exist in the data but haven't been recognized yet. As our analysis techniques improve, and as we think more carefully about what we're looking for, we might find evidence that's been hiding in plain sight all along. The interplay between theory and experiment is what drives physics forward. Theorists develop mathematical frameworks that make predictions about how nature should behave. Experimentalists design tests to check whether those predictions are correct. When experiments confirm predictions, our confidence in the theory grows. When experiments contradict predictions, we know something is wrong with the theory and we need to revise or replace it. When experiments reveal something completely unexpected, it opens new frontiers for theoretical exploration. The greatest advances often come from surprises, from nature telling us something we weren't expecting. The Standard Model of particle physics, our most successful theory of how particles and forces work, emerged from exactly this kind of dialogue between theory and experiment spanning the 20th century. In the 1930s, physicists discovered that beta decay, a type of radioactivity where neutrons transform into protons, seemed to violate energy conservation. Energy appeared to be missing. Wolfgang Pauli proposed a radical solution. An invisible particle, which he called the neutrino, was carrying away the missing energy. This seemed like a desperate move, inventing an undetectable particle just to save a theoretical principle. But Pauli was right. Neutrinos were eventually detected in 1956, more than 2 decades after Pauli's prediction, confirming that nature does conserve energy after all. Similarly, the omega- particle was predicted in 1962 based purely on mathematical patterns in how particles group together. Physicists Murray Gell-Mann and Yuval Ne'eman independently proposed a classification scheme called the Eightfold Way, which organized hadrons, particles that feel the strong nuclear force, into geometric patterns based on their properties. One pattern had a gap where a particle with specific properties should exist but hadn't been seen. Gell-Mann predicted this omega- particle and calculated its properties. In 1964, experimentalists at Brookhaven National Laboratory found it exactly where and how the theory predicted. This triumph validated the Eightfold Way and led directly to the quark model, the idea that hadrons are made of smaller constituents. The Higgs boson followed a similar trajectory. Proposed in 1964 by Peter Higgs and others to explain how particles acquire mass, it took 48 years and the construction of the most expensive scientific instrument ever built, the Large Hadron Collider, to finally discover it in 2012. The Higgs was the final piece of the Standard Model, confirming a theory that had been developed over decades based on mathematical consistency and symmetry principles. These examples show that physics can make predictions that initially seem outlandish but turn out to be true. They also show that confirming or refuting theoretical predictions can take decades and require enormous investments of time, money, and intellectual effort. The search for tachyons fits this pattern. The theoretical groundwork has been laid. The mathematical framework exists. The predictions, while still somewhat vague because different theories make different specific claims, can, in principle, be tested. What's needed now is the right experiment or observation, the breakthrough that either confirms tachyons exist or places such strict limits on their properties that they're effectively ruled out. One particularly interesting avenue for tachyon research involves the foundations of quantum mechanics itself. Quantum mechanics is spectacularly successful at predicting experimental results, yet its interpretation, what it actually tells us about reality, remains controversial even after a century of debate. The famous wave-particle duality says that quantum objects behave sometimes like particles and sometimes like waves. The uncertainty principle says you can't simultaneously know certain pairs of properties like position and momentum with arbitrary precision. Quantum entanglement allows particles separated by vast distances to influence each other instantaneously in ways that Einstein called spooky action at a distance. That last point, entanglement, seems to involve faster-than-light connections between particles. When you measure an entangled particle here, you instantly affect its partner over there, even if it's on the other side of the galaxy. This has been confirmed in countless experiments and is now used in quantum cryptography and emerging quantum computing technologies. But crucially, you can't use entanglement to send information faster than light. The correlations between entangled particles are perfect, but they're random. You can't control what measurement outcome you get, so you can't encode a message. When you analyze the mathematics carefully, quantum mechanics preserves causality, even though it allows these spooky correlations. Some physicists have wondered whether tachyons might play a role in quantum entanglement or in the quantum measurement process. When you measure a quantum system, its wave function, the mathematical description of all its possible states, collapses into one definite state. This collapse seems to happen instantaneously across space, which looks like a faster-than-light process. Could tachyons be involved in propagating the collapse? This is highly speculative, and most physicists would say no, that the collapse is better understood as a change in information rather than a physical process requiring a mediating particle. But the question illustrates how tachyons might connect to deep mysteries in quantum foundations. Another connection involves quantum field theory in curved spacetime, the marriage of quantum mechanics and general relativity. This framework predicts that empty space isn't really empty but filled with quantum fluctuations, virtual particles that pop in and out of existence too quickly to observe directly. Near black hole event horizons, these fluctuations can become real through the Hawking radiation process I mentioned earlier. In certain exotic spacetimes, particularly those involving rotating or charged black holes, the mathematical structure of quantum fields can become complicated in ways that might involve tachyonic modes. These aren't real tachyon particles zipping around, but mathematical solutions to equations that have tachyonic character. Studying these solutions helps physicists understand how quantum fields behave in extreme gravitational environments and might eventually contribute to developing a complete theory of quantum gravity, the holy grail of theoretical physics that would unify quantum mechanics and general relativity into a single, consistent framework. String theory, loop quantum gravity, and other approaches to quantum gravity all grapple with how to describe spacetime at the smallest scales, where quantum effects and gravitational effects are both strong. Tachyons appear in various forms in these theories, sometimes as problems to be solved, and sometimes as tools for understanding dynamics. The relationship between tachyons and the structure of spacetime itself is profound. In general relativity, spacetime is dynamic, warped by mass and energy. Massive objects create curves in spacetime that we experience as gravity. Light follows geodesics, the shortest paths through curved spacetime. If tachyons exist, they'd follow different curves, paths that dip into regions of spacetime geometry that slower particles can't access. In a sense, tachyons would reveal aspects of spacetime structure invisible to everything else. Think of it like this. Imagine spacetime is a landscape with hills and valleys. Ordinary matter and light travel along paths determined by the slopes, always rolling downhill, in a sense defined by the metric, the mathematical description of distances and angles. Tachyons might be able to take shortcuts, tunneling through hills or flying over valleys in ways that reduce their travel time below what light can achieve on the surface. This is a rough analogy, but it captures the idea that tachyons could provide information about space-time geometry that we can't get any other way. Some speculative theories propose that space-time might have more than 4 dimensions, with the extra dimensions curled up so small we don't notice them in everyday life. String theory typically requires 10 or 11 dimensions total. If extra dimensions exist, particles might be able to move through them, potentially taking shortcuts that look like faster-than-light travel from our 4-dimensional perspective. Imagine ants crawling on a garden hose. To an ant, the hose looks like a 1-dimensional line extending forward and backward, but there's also a circular dimension around the hose that the ant could crawl. If 2 ants are at different points along the hose and one takes a shortcut through the circular dimension while the other crawls along the length, the shortcut might be faster. In higher dimensional space-time, tachyonic behavior might emerge from ordinary motion through extra dimensions. A particle moving normally through 10-dimensional space might appear to us, limited to perceiving 4 dimensions, as moving faster than light. This reinterprets tachyons not as exotic particles, but as ordinary particles whose full motion we can't see because we're dimensionally blind. This is beautiful because it transforms a weird phenomenon into a geometric fact about the structure of space itself. Testing for extra dimensions is challenging because if they're curled up at scales smaller than we can currently probe, they'd be invisible to our experiments. The LHC has searched for signatures of extra dimensions by looking for missing energy, particles that might escape into extra dimensions and disappear from our 4-dimensional detectors. So far, nothing conclusive has emerged, which places limits on how large extra dimensions could be if they exist at all. But we've only scratched the surface of possible energy scales and configurations. Future colliders, if they're ever built, could probe higher energies and potentially reveal extra dimensions or other exotic aspects of space-time structure. All of this brings us back to a fundamental question. What is space-time really? Is it a smooth continuum infinitely divisible, or does it have a discrete structure at the smallest scales, pixels of reality that can't be subdivided further? Is time fundamentally different from space? Or are they truly unified as Einstein proposed? Does space-time emerge from something more fundamental, or is it the basic fabric from which everything else is built? These questions have occupied physicists for over a century, and we still don't have definitive answers. Tachyons, whether they exist as particles or merely as mathematical structures in our theories, force us to confront these questions in new ways. They challenge our intuitions about causality, time, and the maximum speed of information transfer. They appear in theories at the edge of our understanding, in contexts involving quantum gravity, cosmology, and high-energy physics. Whether tachyons turn out to be real or just theoretical artifacts, thinking about them deepens our understanding of the laws governing reality. There's a philosophical dimension to all of this that's worth acknowledging. Science isn't just about collecting facts. It's about constructing frameworks for understanding how facts relate to each other, how patterns emerge, how predictions can be made. The scientific method is powerful because it combines creativity with discipline. Scientists are free to imagine wild possibilities, to propose radical ideas, to think outside conventional boundaries. But every idea must eventually face empirical testing. Nature is the ultimate arbiter of truth in science, not authority, not tradition, not intuition. This is why physics can make progress on questions that philosophy has debated for millennia. Philosophers have argued about the nature of space, time, matter, and causality since ancient Greece. These debates produced valuable insights, but no definitive resolutions because they lacked a mechanism for deciding between competing views. Physics provides that mechanism through experiment. You don't just argue about whether space is absolute or relative, you design tests like the Michelson-Morley experiment that check whether Earth's motion through space produces detectable effects. When the experiment says no, you develop new theories like special relativity that explain the result. The same approach applies to tachyons. You don't just debate whether faster-than-light particles could exist. You calculate what properties they'd have, predict what signatures they produce, build detectors to search for those signatures, and let nature tell you the answer. This process takes time, often decades or longer, but it converges toward truth in a way that pure reasoning never can. This is the great strength of science and why it's produced such spectacular advances in understanding the natural world over the past few centuries. But science also requires humility. We must always be prepared to be wrong, to discover that our most cherished theories are incomplete or incorrect. The history of physics is littered with beautiful ideas that turned out to be false. The luminiferous ether, a substance that supposedly filled space and carried light waves, was disproven by the Michelson-Morley experiment and eliminated by special relativity. Steady-state cosmology, which proposed that the universe has always looked essentially the same, was demolished by the discovery of the cosmic microwave background, showing the universe has evolved from a hot, dense state. Cold fusion, the claim that nuclear fusion could occur at room temperature in a simple apparatus, turned out to be experimental error and wishful thinking. Science is self-correcting. When experiments contradict theory, we change the theory. When new observations don't fit existing frameworks, we develop new frameworks. This can be painful for individual scientists who've invested years in ideas that turn out to be wrong, but it's how science as a collective enterprise makes progress. The goal isn't to be right by stubbornly defending your pet theory, it's to understand how nature actually works, even if that means admitting you were mistaken. So where does this leave us with tachyons? As of 2026, they remain a fascinating theoretical possibility backed by increasingly sophisticated mathematical analysis, but lacking experimental confirmation. The pendulum of scientific opinion has swung somewhat in their favor recently, thanks to work showing they're compatible with fundamental principles when properly analyzed. But compatibility isn't proof of existence. Many things are theoretically possible that don't actually occur in nature. The electron could have had a different mass than it does. The universe could have had different laws of physics entirely. The fact that we can write down consistent equations describing tachyons doesn't mean nature chose to implement them. What we need, ultimately, is data. We need observations that can't be explained any other way, signatures that unambiguously point to faster-than-light particles. This is a high bar, as it should be. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. The claim that particles can exceed light speed is extraordinary, given everything we know about physics, so the evidence needs to be rock-solid, reproducible, and resistant to alternative explanations. This is why the scientific community is appropriately skeptical while remaining open to the possibility. Skepticism isn't the same as close-mindedness. Skepticism means demanding good evidence before accepting surprising claims. Open-mindedness means being willing to change your views when good evidence arrives. The combination of skepticism and open-mindedness, held in balance, is what allows science to avoid both gullibility and dogmatism. Let me paint a picture of what discovery might look like if tachyons do exist. Perhaps a neutrino observatory detects particles arriving from a supernova several hours before the light reaches Earth, far earlier than can be explained by the neutrino's journey through the star. Multiple observatories confirm the timing anomaly, ruling out instrumental errors. Theoretical physicists analyze the data and show that the arrival times perfectly match predictions for tachyonic neutrinos with a specific imaginary mass-squared value. Additional supernovae provide confirming evidence with consistent timing patterns. Or perhaps the Large Hadron Collider's successor, a proposed future circular collider with 7 times the LHC's energy, begins operations in the 2040s and discovers particles with strange properties. They appear to move backward in time in certain reference frames, they carry imaginary mass, and they produce characteristic signatures predicted by tachyon theory. Experiments around the world replicate the discovery. Within a decade, tachyon physics becomes an established field with hundreds of researchers exploring the implications. Or perhaps a gravitational wave observatory detects ripples from colliding black holes, and coordinated observations reveal additional signals arriving slightly before the gravitational waves, signals that match predictions for tachyonic gravitational radiation. Further observations strengthen the case until the evidence becomes overwhelming. Astrophysicists realize that tachyons have been part of the universe all along. We simply hadn't developed the right instruments to detect them until now. Any of these scenarios would trigger a scientific revolution. Physics departments would need to revise their curricula to include tachyon dynamics. Astronomy would gain a powerful new tool for exploring the cosmos. Technology companies and military agencies would immediately begin investigating whether tachyons could be harnessed for communication or other applications. Philosophers would debate the implications for free will, causality, and the nature of time. Science fiction would have a field day imagining futures where faster-than-light travel is possible, but it's equally possible that tachyons simply don't exist. Perhaps nature has some reason, not yet understood, for forbidding faster-than-light particles despite their mathematical consistency. Perhaps the universe could have contained tachyons, but the particular way quantum fields settled into their current configurations during the early universe excluded them. Perhaps tachyons require conditions so extreme, energies so high, or space-time curvatures so intense that they're effectively impossible to produce or observe with any technology we could conceivably develop. If decisive evidence eventually rules out tachyons, that would also be valuable. Negative results are still results. Knowing what doesn't exist narrows the space of possibilities and guides future research. The Michelson-Morley experiment's negative result, finding no evidence for the ether, was crucial for developing special relativity. Countless searches for proton decay, predicted by some grand unified theories, have found nothing, placing strict limits on proton lifetime and constraining theoretical models. LIGO spent years searching for gravitational waves before detecting them in 2015. Those years of null results weren't wasted because they developed the technology and techniques that eventually succeeded. The search for tachyons, regardless of outcome, advances physics. It forces us to think carefully about causality, relativity, and quantum mechanics. It pushes experimentalists to develop more sensitive detectors and more sophisticated analysis methods. It connects to broader questions about the structure of spacetime and the nature of fundamental particles. Even if we never find a tachyon, the journey will have been worthwhile because it deepens our understanding of the universe. There's something profound about humanity's quest to understand reality at its most fundamental level. We evolved as apes on the African savanna, selected by natural selection for abilities that helped us survive and reproduce in that specific environment. Our brains developed to track predators, find food, navigate social hierarchies, and raise children. Nothing in our evolutionary history prepared us to understand quantum mechanics, general relativity, or particle physics. The universe had no obligation to be comprehensible to creatures like us. Yet somehow, against all odds, we can understand it. We've developed mathematics that describes how particles and fields behave. We've built instruments that detect phenomena far beyond the reach of our senses. We've constructed theories that make predictions confirmed by experiments. We've traced the history of the cosmos back to fractions of a second after the Big Bang. We've identified the particles and forces that make up everything we see. This is staggering when you think about it. 3 pounds of neural tissue, evolved for survival on prehistoric plains, can grasp the behavior of black holes, the expansion of space-time, and the quantum fluctuations of fields. Physics is humanity's greatest intellectual achievement precisely because it's so far removed from our everyday experience and intuitions. Understanding that Earth orbits the Sun required overcoming powerful impressions that the ground is stationary and the Sun moves across the sky. Understanding that solid matter is mostly empty space required accepting that our senses deceive us about the nature of objects. Understanding that time flows at different rates for different observers required abandoning deeply ingrained notions of absolute simultaneity. At every step, physics has revealed that the universe is stranger, more subtle, and more beautiful than common sense suggests. Tachyons, if they exist, would be another step on this journey into strangeness. They'd show us that even light speed, that seemingly absolute cosmic speed limit, might not be the final word. They demonstrate once again that nature is more clever and more surprising than we imagine. But even if tachyons don't exist, we've learned something important by taking them seriously. We've learned that faster-than-light particles are compatible with the mathematical structure of relativity when analyzed carefully. We've learned that causality in field theory is more subtle than simple notions of cause preceding effect. We've learned that imaginary mass doesn't lead to immediate contradictions but requires thoughtful interpretation. We've learned that many phenomena dismissed as impossible might simply be improbable or undetected. Science progresses not just through dramatic discoveries, but through careful analysis, patient observation, and incremental refinement of understanding. The vast majority of scientific work isn't revolutionary breakthroughs that overturn everything we thought we knew. It's painstaking measurement, detailed calculation, systematic exploration of parameter space, and careful checking of results. It's graduate students spending years collecting data, postdocs analyzing that data with sophisticated algorithms, and senior researchers synthesizing findings into coherent pictures. The search for tachyons exemplifies this kind of work. No single observation will definitively prove they exist unless the signature is overwhelming and unambiguous. Instead, evidence will accumulate gradually. Refined theoretical predictions, improved experimental limits, possible hints from multiple independent sources, and eventually, if we're lucky, a preponderance of evidence that convinces the community. Or evidence will accumulate that they don't exist, stronger and stronger limits on their properties, explanations for apparent anomalies that don't require tachyons, and theoretical arguments for why they shouldn't be real. Either way, the process takes time. The announcement in 2024 that tachyons are compatible with relativity is one step on a long journey, not the final destination. Future steps will include more detailed theoretical analysis, specific predictions for different tachyon models, experimental searches targeting those predictions, and ultimately judgment by nature through the results of observations. This might take another decade or another century or longer, but eventually we'll know. In the meantime, we can appreciate the beauty of the physics involved. The equations describing tachyons are elegant, connecting imaginary mass to superluminal velocity in ways that respect the fundamental structure of spacetime. The extended field theory formalism that Dragon's team developed is mathematically sophisticated, showing how to properly handle field boundary conditions in ways previous analyses missed. The connections to cosmology, quantum mechanics, and black hole physics reveal deep relationships between different areas of physics. This is what makes physics exciting even when we don't have definitive answers. The process of exploring possibilities, developing frameworks, and connecting ideas across different domains is intellectually thrilling. Each paper published, each experiment conducted, each observation made adds a piece to the puzzle. Some pieces fit together smoothly, revealing patterns. Other pieces seem contradictory, pointing to gaps in understanding that need to be filled. Gradually, patiently, collectively, physicists around the world build up a picture of how nature works. If you made this far, make sure to subscribe to the channel and give this video a like. And I am sure you will love this video at the left side of the screen. This is why no civilization could ever spread across the galaxy. Learn about the crushing energy requirements that make even 1% light speed travel require more power than civilization produces in years, why self-replicating von Neumann probes face insurmountable reliability and coordination failures, how the dark forest hypothesis suggests advanced civilizations might be hiding in terrified silence, and much more.